Okay, we're going to take a look at the notes for section 4.2, which is building on what we did in 4.1. If you remember, 4.1 was all about forcing functions being applied to our harmonic oscillator. 4.2 is going to look at a specific kind of forcing function. We're going to focus on the sinusoidal or periodic forcing function. And so in 4.1 we started off with something that looked like this. And if you remember, the left-hand side, this is our harmonic oscillator equation. And the right-hand side, that amounts to our forcing function. So the left-hand side is telling us all the information we need to know about our harmonic oscillator, but the right-hand side is telling us about whatever kind of outside forcing function there is. And the key for us in this case, in this section, we're going to be looking at and paying attention to only situations where we have damping. Right? Later on, we're going to take a look at some kind of more particular situations, what happens when maybe the damping is small. But for right now, we're going to focus on a damped harmonic oscillator that has some outside forcing function. And so the first little bit says, what would a forced harmonic motion look like if an external force was based on a sine or a cosine function? And if you remember, sine or cosine, they're going to be, this kind of function over time, right? And so that would be our f of t versus t. And since our sine or cosine function is going to be oscillating back and forth, that means that the force must be changing direction. With time, periodically. And so you could think of it as a push, and then a pull, and then a push, and then a pull, so on and so forth. This idea being that if you have a forcing function that is periodically changing direction, we could model that with a sine or a cosine. And so one of the kind of more interesting features of this is that in the long run, and of course in the long run that's mathematical code for as t approaches infinity, only the periodic part of this, the periodic function, remains to affect the motion. And that's because we have damping, right? As long as there's damping going on, we know that there's going to be, it's just going to die out over time, and all that we're going to have left is this forcing function. And the other thing that's worth noting is if you recognize that sine and cosine both have this feature where they oscillate back and forth, you know that if you were to average out the force over time, and that's going to be equal to 0, right? It's basically saying that you're going to have as much push as you do pull. And so we're going to start by looking at the situation that's kind of modeled up above, this idea of a damped, forced harmonic motion. And so the next little line down on this page says we're going to take a look at damped, which of course from above we know that that means the P is not equal to 0. And forced, and if you remember the forced up here, that guy is saying G of t is not equal to 0. So the conditions of our first couple of examples, well, most of the examples in this section are where we have damping and some kind of force. Specifically, the damping is going to be significant and the forcing function is going to be sinusoidal or periodic in nature. So we're going to take a look at our first example, differential equation. And remember, we have really three main steps in order to find the solution to this. You've got at the bottom of this, or at this example right here, you have on the left-hand side, if you kind of cover up the forcing function, you've got a homogeneous differential equation if that's equal to 0. It's not equal to 0, so the whole thing itself is non-homogeneous. And so what we need to do is find the general solution of this unforced dE. And really that unforced dE, this is the entire, oops, a little fuzzy. This is our homogeneous differential equation, right? And that's the left-hand side, if you want to think of it that way, of the equation. And so the first step in this process, as we spent a lot of time doing in 4.1, is find our homogeneous portion of the solution. And we do that by taking a look at just the left-hand side of the equation and then turn it into our, basically our characteristic polynomial and say that this thing, when it's translated into characteristic polynomial, is s squared plus 3s plus 2. And because we are interested in it being the homogeneous version, then it's going to be equal to 0. And because we know this thing factors, nice and neat, this becomes s plus 1 times s plus 2 equals 0, which means we have two possibilities. One of them is s equals -1. The other is s equals -2. So that means that there's two parts. You can think of it as two parts to my general solution. The general solution for my homogeneous part is going to be the combination of these things written in exponential form, so with a constant in front of them. So k1 e to the minus t for the first one, plus k2 e to the minus 2t. Now, keep in mind, we've gotten so good at being able to solve these homogeneous differential equations that just looking at this left-hand side, we can see that we can factor it. We have our two s values that gives us two particular solutions, which we toss in here with a constant in front of them, and that gives us our homogeneous portion, right? So that's the easy part, I guess you could say, of our differential equation. The second part, the next part, is figuring out any one particular solution for the forced differential equation. So we need to find a particular solution. If you remember, any one particular solution, really we're looking for the easiest to find one. We're looking for this y sub p, right? And so we do that by coming up with a good guess. And if you remember, the equation that we're dealing with looks like this. It basically says take the second derivative of your solution plus 3 times the first derivative plus 2 times the solution itself, and that's just going to equal sine of t. Now the problem with saying, oh, okay, then that means whatever my guess has to be is just going to be some constant times sine. The first derivative of sine is cosine. So I'd be introducing a cosine if I just had a guess of sine. So what we're going to try to do is avoid the hiccup of having a problem with our guess by, rather than just saying it's a times sine of t, we're also going to introduce the idea of a cosine term. So b times cosine of t. And you'll notice that the coefficient that's in front of the t in this case is the same as what's inside the forcing function. It's the same coefficient as inside the forcing function. Right? So that's important to note. So if it were, for example, if our forcing function were sine of 3t, then we would make those a sine 3t and b cosine 3t, but we're going to keep the same coefficient there. And that means that now we can come up with our y prime and our y double prime, because we need both of those to be able to substitute it back into the equation. So if you are paying attention, the first derivative of a sine t is a cosine t, and the first derivative of this term is going to be minus b sine t. And then, of course, taking the second derivative gives us negative a sine t minus b cosine t. So we have our guess, the first derivative of our guess, and the second derivative of our guess. And so we should be able to find the values of a and b that make this guess true. And remember, the idea of making something true in mathematics, we can check by substituting into the equation. So I should be able to substitute these values into the equation. And if you remember, the equation from the previous page was take the second derivative, which is negative a sine t minus b cosine t, plus 3 times the first derivative, which is a cosine t minus b sine t. And it was then plus 2 times the function itself, a sine t plus b cosine t. And all of that has to equal on the right-hand side just plain old sine t. Now, we've used a similar trick before, but you probably noticed that the right-hand side of this equation is just the sine function, which means that the coefficient that's on this guy right here, 1, has to be the sum of all the sine terms on this side. So what I'm going to do is I'm going to underline all of these in the same color and say that sine, that's a sine term, this is going to be a sine term, this is going to be a sine term, and that's a sine term. And all of these have to play nice together and give me one equation. And then there's another equation that is saying, okay, well, what about the cosine terms? And so I'm going to use a different color here so it shows up a little bit better. There's a cosine term, there's a cosine term, there's a cosine term, but there's no cosine term over here. So the question is, what's the cosine term over here? Well, it's just 0. So I'm going to tack on plus 0 cosine t, and I'm going to say all 4 of these have to play nice together. And so I really actually have 2 equations going on at the same time. I'm just going to pay attention to their coefficients. So you'll notice this is all the sine terms. And so this is negative a. And then this is going to be plus 3 times negative b. So minus 3b. And the next sine term is here, so it's 2a. And then this side is just equals 1. So there's one equation that's in terms of the sine coefficients, right? And so these are the sine coefficients. And that has to be true. But the green underlines also have to be true. And so if we pay attention to the cosine coefficients, we come up with an equation that looks like this. Negative b plus 3 times a, so that's plus 3a, and then 2 times b plus 2b. And on the other side, it's got to equal 0, because all those coefficients have to add up to having literally no cosine term. So I actually have 2 equations with 2 unknowns, the a value and the b value, that I can now manipulate. And so what I'm going to do is I'm going to manipulate this guy, play around with him, and see if I can solve it for something that makes sense. So in this case, I'm going to have a negative a plus 2a, so that's just a, equals, the other side is going to be 1 plus 3b. Right? So I've got a equals 1 plus 3b from this equation right here, and I can toss this thing into the other equation if I want. Or I could solve this one for b and then toss it into there. It doesn't matter. It just so happens that it's pretty easy to solve this one for b, because negative b plus 2b. So I'm going to have b equals, move the 3a to the other side, negative 3a. And so now I can take this value for b, substitute it in here, and solve my system. Right? So with a little bit of effort, I can find out that, let me scoot this up a little bit. Kind of toss that in there, and I get a equals 1 plus 3 times negative 3a. Right. And so playing around with this, I find out that a equals 1 minus 9a. Move the 9a to the other side, add 9, and I wind up with a is equal to 1/10. And if I know a is equal to 1/10, I can bring that back over here and find out that b is equal to negative 3 times 1/10, or b is equal to negative 3 tenths. So that means there's an A value and a B value that make this guess that I started with way at the top here, that make that guess true. And only one A value and only one B value. So after all is said and done, I can say my particular solution that 100% works is 1/10 times the sine of t plus, minus 3/10. Minus 3/10 times the cosine of t. Now, if you were to take this right here, toss it back into your original differential equation, the one from the previous page, and say, I'm going to toss that into this equation, it would make the left-hand side 100% equal to just plain old sine of t. Doesn't seem like it, but it works. So after all is said and done, I now have my particular solution. I have my homogeneous solution from the previous page, and so I can add those two together and get my general solution. So very similar to what we did in the last section here. I can find out that y of t is equal to my, let me scoot up here, my homogeneous solution plus this particular solution that I found. That means my overall general solution is k1 e to the minus t plus k2 e to the minus 2t plus this whole solution right here, that whole particular solution, 1/10 sine t minus 3/10 cosine t. And so this right here is the general solution for that differential equation. And of course, we can plug in initial conditions. We can figure out what K1 and K2 are for particular situations. And also keep in mind that this is the general solution, and so over time, these two terms, no matter what the K1 and K2 values are, these two terms are going to disappear because they're exponentially decaying. But these two terms will not. These two terms are going to be the long run part of our solution. In other words, as time approaches infinity, it's going to behave like 1/10 sine t minus 3/10 cosine t. These two terms just kind of disappear. The part of the general solution that comes from the harmonic oscillator itself, the homogeneous part of the solution, kind of fades away. That natural state kind of fades away, and we're left with the steady state part of the solution. So down here at the bottom of the page, it says, of course, if we had initial conditions, we can generate a particular solution that allows us to figure out what's going on. So a couple of things that we'll kind of pay attention to as we move on is that our forcing function in this case was a sine function, but the long run solution equation turns out to be both sine and cosine. So it's not so simple to just say, oh, the forcing function is sine. That means that the particular solution is going to be a sine function. It's sometimes a little bit trickier than that. So we'll stop here, and I'll let you take a look at the next video to see what's going on with the next example.